So let's talk about the beta distribution. So we'll say that x is distributed beta with parameters alpha and beta. Seems kind of strange, but yeah, that's what we're doing here. The name of the distribution is beta, and its parameters, at least according to your book, are alpha and beta. You could use S and T, whatever you want, smiley face and frowny face. Okay, we'll use alpha and beta. This distribution only depends on these two parameters. They're both non-negative, and it's said to be distributed beta if its density function looks like this. Okay, it's going to be as a function of x. It's x raised to the alpha minus 1 times 1 minus x to the beta minus 1 all over some other function b, we'll call it, evaluated at alpha and beta, and multiply the whole thing by the indicator that x is in the closed unit interval. Okay, what is that stuff in the denominator there? Stuff in the denominator is a very important function. It's called the beta function, and we'll actually write it as b as a function of alpha and beta, like that. And this guy is defined to be the integral from 0 to 1 of s raised to the alpha minus 1 times quantity 1 minus s raised to the beta minus 1 ds. And in fact, it's possible to show that all this is equal to, guess what, gamma of alpha times gamma of beta all over gamma of alpha plus beta. Okay, so maybe you could try to show this. Can you show this? Try to show that. Okay, you should try to show that. It'd be great. The CDF, the cumulative distribution function for a beta random variable, can't be written in closed form, but of course, by definition, it's the probability that the random variable is less or equal to little x, like that. And of course, I can't get an expression for it for sure, right? It's just going to be, let's see, from negative infinity up to, say, little x, and then I'll stick in my probability density function there, right? I'll use s as my dummy variable though this time. Let's see, because I've got an x up here. So s raised to the alpha minus 1 times 1 minus s raised to the beta minus 1 all over the beta function evaluated at alpha and beta. Okay, I know that sounds kind of weird, but yeah, that's how it goes. And this is for say ds. This is for s in for x in 0 to 1. Okay, and of course it's equal to 0 for x less than 0 and 1 for x greater than 1. Okay, so you may notice that this beta function, that the beta random variable itself can only take on values in the closed unit interval from 0 to 1. So what's it good for? Well, it turns out that beta random variables can be good for modeling proportions. They play a fundamental role in Bayesian statistics. We're not going to do much with them, at least not in this class, but you should get exposed to them. Oh, and by the way, sometimes we denote the CDF of the beta function, sometimes written like that, with an I, and with the domain variable there is down in the subscript of alpha and beta like this, and this is called the incomplete beta function. Okay, the incomplete complete beta function. Okay. Now, one can show, turns out, one meaning you, with integration by parts, that this incomplete beta function actually works out to be the sum, k goes from alpha up to n of n choose k times x to the k times 1 minus x to the n minus k. Okay? Yeah, and you should note that all this stuff in here looks awfully familiar. This is the probability, it's the probability mass function for a binomial random variable with parameters n and x. Okay, x here is the success probability. See that? Okay, so maybe you could try to show that this is true using integration by parts. All right. Now, here's a theorem for you. Let's see if we can find the expected value of a beta random variable. I bet we can. So, theorem says that if x is distributed beta with parameters alpha and beta, again with alpha and beta must be greater than 0, this implies that the expected value of x is alpha over alpha plus beta. And also we can get an expression for the variance of x, turns out to be alpha beta over alpha plus beta quantity squared times alpha plus beta plus 1. Okay. Now, I'm not going to prove the variance. I'll leave that to you for an exercise. I think it's in your homework set. I will get the expected value because it's easy. Okay. So here's the proof of the mean. Okay. So the expected value is, of course, by definition, this guy is the integral over all reals of x times the density function, right? And then, so that's just the integral over all reals of x times, I'm going to sub in my density function there now, right? Okay, which is x to the alpha minus 1 times 1 minus x to the beta minus 1. All of that over the beta function evaluated at alpha and beta. I'm going to multiply all that by my indicator function of x being in the unit interval, 0 to 1, so dx. Okay. See that? Now, you can see what I can do right away here. I can pull this x into this other factor and just have x to the alpha. And I can also use this indicator function to simplify the integrand. Right? I can remove this indicator function provided I change my integration limits to be 0 to 1. Right? So this just comes out to be, and in fact, if it's okay with you, I'll go ahead and take out that beta function out of the bottom, like we did when we were working with the gamma distribution. Oftentimes we'd take that out, right? Go ahead and pull that out, remove the indicator function, and change my limits of integration. And then I've got x to the alpha times 1 minus x to the beta minus 1 dx. Okay? Now, take a look at this. This is the beta function, right? This integral there is the beta function. I'm gonna grab this stuff from over here, right? So this is beta of alpha beta. This integral right here, if you look back at the definition of the beta function, you should see that it is in fact beta of alpha plus 1. and beta. Okay. All right. Now, at this point, I'm going to use that thing that we didn't actually show, but I asked you to show. Remember that? Let me move back over here. My notes here. Turns out you can show that beta of alpha and beta is gamma of alpha times gamma of beta over gamma of the sum. I'm going to use that back over here. Okay? So I've got beta of alpha plus 1. Just to remind you, it's beta of alpha plus 1 and beta all over beta of alpha beta, right? Using that, using the gamma expressions, this is gamma of alpha plus 1 times gamma of beta all over gamma of alpha plus 1 plus beta times, let's see, down here, this is going to be gamma of alpha times gamma of beta. And then on the top, I'm going to have gamma of alpha plus beta, right? Now look, these guys are going to cancel, right? And so then this is actually, this just turns out to be, so it's gamma of alpha plus 1 times gamma of alpha plus beta over gamma of alpha plus 1 plus beta times gamma of alpha, right, which you should see that turns out to be alpha over alpha plus beta.